All right, ladies, so we are continuing in section 10.1. We just started in class before the exam, but let's look at example 3. So this, I want to introduce a recursive sequence. Now let's just first, before I introduce and state what exactly a recursive sequence is, let's just look at this sequence here. So a sub n equals 1 over 2 times n minus 1 for n equals 1, 2, 3. So let's find a sub 1, a sub 2, and a sub 3. Well, a sub 1 is just going to be 1 over 2 times 1 minus 1. Almost reminds us of a function, correct? Hopefully you see that. So that's 1 over 1, so that's just 1. A sub 2 is what? 1 over 2 times 2 minus 1, so that's 1 over 3, 1/3. And then a sub 3 equals 1 over 2 times 3 minus 1, which is 1/5. Okay, so now what we want to do is what's called a recursive sequence. And recursive sequence basically involves having to go back to look at previous terms. So in part A, we're calling a new sequence B sub n, and it's equal to a sub n plus 1. So this is an example of recursive sequence, and it's recursive. And so let's find the first 3 terms. Okay, let's find the first 3 terms of that. All right, well, b sub 1, if we substitute in wherever we say n a 1, right? So that's a sub 1 plus 1. Well, we saw for a sub 1, right? A sub 1 was just 1. So that's going to be 1 plus 1 equals 2. So b sub 1 equals 2. B sub 2 equals a sub 2 plus 1. And so that's going to be 1/3 plus 1. So that's 4/3. And then b sub 3 is going to be 1/5 plus 1, which is 6/5. Okay. B, let's look at B, or example B, I should say. Let's say now C sub n is a sub n plus 3. Okay. Pause the video and see what you get for C sub 1, C sub 2, and C sub 3. Okay, welcome back. So you should have received C sub 1 is 4, C sub 2 is 10/3, and C sub 3 is 16/5. Okay, let's look at D sub n equals a sub n squared. All right, so now, I actually already plugged that in for you, but this is a sub 1 squared. Well, a sub 1 is 1, so 1 squared is 1. Again, pause the video and figure out what the other answers are. Okay, so hopefully you receive 1/9 and 1/25. Okay, the last one, and I want you to try this one on your own. E sub n, which is 2a sub n minus a sub n plus 1. So I want you to try these. I'm just going to give you the final answer, and I want you okay, but your final answer should be 5/3, 7/15, and 9/35. All right, so if you did not get those answers on Monday, let me know and we can go back over this in class. Okay, so now if you want to pause the video and write this information down and then come back to the video, you can. So I gave you one definition of a sequence, sort of an ordered list, following ordered list of numbers following a specific pattern. But another definition I want to give you here of a sequence is it's a function, right? And so when we were looking at those recursive sequences, you almost can see how it resembles a function. So a sequence is a function whose domain is a set of integers. F sub n goes from 1 to infinity. Note, since sequences are functions, we can graph them. Okay, right? It's a function. However, this is what you have to remember. That our index n only takes integer values. So we cannot connect the points. Okay, so we treat it like a function, but it's a function whose domains are just a set of integers, and that's very important as we move on, so make sure you remember that. All right, so let's look at this. I think this is example 4, actually. Okay, and so f of n is equal to 1 over n, and n goes from 1, 2, 3, ... I'm just making a table on the left hand side here. I have a table of some values of n. Of course, remember they're integer values. They're actually natural numbers. And so looking at this graph, you see in the dots, hopefully you can see the yellow dots, I graph f of n, right? So this is sort of representing n, and that's f of n. And here, again, we can't connect the points because 1.5 doesn't exist, values in between 1 and 2 doesn't exist. We're just taking on integer values. But what you notice is that these values, right, these values are getting, it's like it's getting a little smaller, not smaller, more closer to the x-axis, right, or that horizontal line here. And so it doesn't make sense to talk about, so when we talk about limits, right, because it's a function, so we talk about limits because we treat it as a function. However, it only makes sense when we talk about a sequence to talk about n as it goes to infinity, right? Because these are distinct points here. So the neighborhoods around it doesn't exist in this particular sequence. So it wouldn't make sense to say the limit as n approaches 1, right? That wouldn't make sense because it's just that dot. It's nothing around it. It's no neighborhood around it. But it makes sense to say, well, as this sequence is going to infinity, do you think what's going on with that? Okay, and so that's very important to note. So let's look at this definition. Again, if you want to pause the video and write this down, you can. But this is the definition of the limit of a sequence. And so we say that the sequence a sub n converges to a limit, call that limit L, if as n goes to infinity, the values of the sequence tends to a finite number L, okay? And if the limit is infinity or does not exist, we say the sequence diverges. So similar to when we talked about improper integrals, right? When we took the limit of improper integrals, which you just had on your exam. Okay, so that's the limit of a sequence. And so example 5 says, well, why don't we go back and look at those sequences that we did in the first 2 examples and see if we can determine whether the sequence will converge or diverge. Okay, so I've sort of written down the sequences here in example 5 for us to look at. Now I'm actually going to look at a couple. So this one, I'll put 2 stars around it. I'll talk about in class because I have to mention something a little bit about factorial, what happens to it. And I added I threw in an extra problem there. So, that's fun. But let's start with, I'm going to start with examples 2 and 4. Okay. And you'll see why in a minute. All right. So in example 2. Okay. So if we let's look at this. So if we take the limit as n goes to infinity of 1 over 2 to the n, well, 2 to the n is an exponential function, right? So what happens as 2 to the n? So 2 to the infinity is going to blow up, right? And what will happen to the entire expression? Well, it's going to go to 0, right? So that means, which is a finite number. So that means this converges, right? So this sequence actually converges to 0. Okay. Well, what about this one? And I did these 2 because they're pretty straightforward, or they should be pretty straightforward for you all. As n goes to, oh my goodness, the stylus is acting up, but we will push through. All right. As n goes to infinity of 2n minus 1, what's happening there? Well, that's going off to infinity, right? So this diverges, right? That's blowing up. Those numbers are blowing up, right? And so it goes off to infinity. Okay. Well, let's look at example 1. The limit as n goes to infinity of n over n plus 1. Well, that's going to go to infinity over infinity. And I know what most of you are thinking, oh, that's an indeterminate form. But it's not, because it's not a function, right? We only talk about indeterminate forms when we're looking at functions, okay? And so this is just infinity over infinity for now. So right now, although we're going to learn something in a minute, but right now all we can do is sort of force factor, which let's see if I talked about that. So I'm going to go to another page here. Okay, so I want to force factor this. So what that means, factor means multiplication. So I want to I'm going to rewrite n as n times 1. And then force factoring, I feel like I talked about this in class, and if I didn't, let me know. But force factoring out that n will give us 1 plus 1 over n. And if you wanted, you could have did this as side work, and so you wouldn't have to write the limit on every line. Well, this becomes a 1. And so now this is 1 over 1 plus 1 over n. Well, what's going to happen? This right here is going to blow up to 0. It's going to go to 0, right? Because you put it's 1 over infinity, which goes to 0. So your final answer is going to be 1, right? So this limit actually converges to 1. This sequence converges to 1. So we can write here that the limit, making it small, let's squeeze this in, the limit as n goes to infinity of n over n plus 1 equals 1. So it converges. Hopefully you have more room in your notes and not like me trying to squeeze it in there. All right, well, what about number 3? What is going on in that problem? And it's actually -1 to the n, I believe, right? Or was it n? Oh, I think you guys in class wrote it as -n like that. I think that's how you guys wrote it in class. I can't remember. All right, so the limit as n goes to infinity of -1 times -n over n plus 1, right? Well, again, this is going to infinity over infinity. And so let's see what's going to happen here. Okay, so I actually had to go back over some things because I forgot that in there. I had to check my notes because something was incorrect. So it should be -1 to the n. Then I think you guys said times -n over n plus 1. So if we look at this limit as n goes to infinity of -1 to the n times -n over n plus 1. Well, what's happening? Just think about this -n is doing what to our sequences? It's making it alternate or oscillate, right? So it's going between positive and negative. And so if it's going between a positive or negative, then will it ever, so here's the question, and this is a very important question. So if it's oscillating between a positive and negative number, will it ever go to converge to an actual number? And it's sort of a yes and no response. And so just think about, what does that mean? Well, it's going to go back and forth, so it won't converge to, it's going to go back between positive and negative. So you think, like, how can it go to something, the same number, if it's positive and negative? And the answer is if it's 0, right? Because if you're coming up, and just think about a sequence, right? And this is very exciting. So if you have a sequence that's converging to 0 there, well, it could be converging to 0 looking like that, right? So, oh, actually, no, I meant something else. Yes, okay. We were rethinking now, the beauty of technology. All right, let's say it's positive, and then it's negative, and then it's positive, and then it's negative, and then it's positive, and then it's negative, but it's getting closer and closer to 0, okay? So that's when it actually will converge to 0. But in this case, this isn't happening, because if you notice the terms in the sequence, so absent, if you don't pay attention to the signs, so omitting those negative signs and just looking at the numbers, 1/2, 2/3, 3/4, 4/5, those numbers are getting large, right? So they're not going to 0. Okay, so this actually, we say it diverges. All right, because the sequence does not exist. On Monday, remind me to show you one. Actually, no, I don't have to wait till Monday. Let's look at number 6. That's why I put that on there. Number 5, I have to tell you some more information about factorials and things, so we can finish that. Remind me to finish that on Monday. But here, let's look at this. Now, this is going to alternate, but if you plot it, and if you want, you can plot it in your notes. It would be nice when you're writing your notes to plot. If you plot, you're going to have positive, negative, and they're getting smaller and smaller. That sequence is getting smaller and smaller. So this actually converges to 0. And again, if you're not sure, let me know. On Monday, Monday, I thought I would be moving on, but I want to do one more day of this, but I'm really looking for you all to look at this as well. So I think I want to give you one more thing before I give you this. Hold on. Okay, so a couple more things and I'm going to end this video, but the limit, so I want to make this note. The limit does not change if we change or drop finitely many terms of the sequence. So in other words, if n starts from 1 to infinity and that limit exists or does not exist, then it doesn't matter if I start the limit from n equals 500 to infinity. It's still going to either converge or diverge depending upon what happened from the start. So dropping off finitely many terms doesn't affect the limit of our sequence. And a theorem in your books, which is really nice, and you're going to love it, because it says if the limit as x goes to infinity of f of x exists, then the sequence a sub n equals f of n converges to the same limit. So this says if you can change your sequence to a function if that limit exists. So if it doesn't, you don't know. And those who are in foundations know that if that if statement isn't met, you can't conclude anything. But if you take your sequence, turn it to a function, take the limit of it, and that limit exists, then that limit is also the limit of your sequence, which is very, very powerful. And so the last example that I'm doing in this video, so I'll finish the rest of the examples on Monday, but find the limit of the sequence n squared minus 2 over n squared. Okay, well, first, let's change this. Oh, we are not writing in yellow. Let's change this to a function, right? So let's change it to x squared minus 2 over x squared. We can actually simplify this function, right? Because we can write this, separate those two, and so that's 1 minus, so we even have that. So let's take the limit as x goes to infinity of 1 minus 2 over x squared. Well, that's going to go, this is going to 0, right? So that's just going to equal 1. So thus, since that limit exists, we can say the limit as n goes to infinity of n squared over 2 over n squared equals 1. Okay, so our sequence converges. What this also means is that if you find that the limit, you can always change it to a function. And if it has the indeterminate form, then you can use L'Hopital. So you can only use L'Hopital's rule when you have that function. So you would need to change it to a function first. I would need you to see those letters change to a function. So I know that you're using L'Hopital because you now know it's a function. Okay. All right, so to save time, I had like different definitions, and I'm like, that's a waste of time in the video when you can just write it out in the book. So I want you to look in the book before Monday. By class on Monday, these should be complete. I don't want you to not have these definitions and theorems. So I want you to look in the book and write out, even if you don't understand what they mean. We'll do some examples on Monday, but I want you to write out the squeeze theorem for sequences, the geometric series, and their limit laws for sequences, bounded from above and the upper bound, write that definition out. Bounded from below and the lower bound, write that definition out. What does it mean for a sequence to be bounded? Monotonic sequences, and then increase and decrease in sequences. And let me just say, and I want to reiterate, if you are a math major, you need to know these like the back of your hand eventually when you get to real analysis in these upper level classes. But even if you are not, you still need to understand these because you might see these terminologies in other courses. So make sure you write these notes down before class on Monday, and I will see everyone on Monday.